This is section 5.3, the Fundamental Theorem of Calculus. We'll start by stating the theorem. Let f be a continuous function on an interval I containing a number a. Well, in this case, we'll just say our interval is the whole real number line, and let's just put a somewhere on the line. So a is fixed, and the curve y equals f of x, or f of t, I've drawn it here. Y equals f of t is a fixed curve, and a is the bottom limit of integration. Then we define a function of x where x varies. For example, if we pick x right here, a sub f of x will be determined by where we pick x, and it will be the signed area from a to x. This function is defined for every x in the interval, and a sub f prime, this area function here, a sub f of x is that area. The derivative of that function, as we have observed in section 5.2, is in fact the integrand function. Another way to think about this is that the rate of change of area under the curve, the rate of change is given by the curve itself, y equals f of x. It's very important that you know how to read the textbook and to be able to say these things properly. So here is two other ways to write the conclusion of the fundamental theorem. Before, we just said that a sub f prime of x is equal to little f of x. Notice we're not putting t in here, we're putting x. If I told you that a function was 3x squared, you would never say that its derivative was 6t, would you? Is 6x. And similarly, we use x's in both places here. Another way to say this same thing is, and watch carefully how we read it, the derivative with respect to x of a sub f of x is f of x. Or, equivalently, the derivative with respect to x of the integral from a to x of f of t dt is f of x. Here's an example of the type of problem you'll be asked in this section. Every single problem is just testing to see if you know the fundamental theorem and what it says. And of course, it requires previous knowledge from Calc 1 and Pre-Calc. So here we have a function given to us. Capital F of x is the integral from 1 to x. Notice this brings to mind immediately the fundamental theorem. In fact, when I see something like this, I don't even stop and see what it's asking. I just say, oh, I know one thing right away. Capital F prime of x is the cube root of x squared plus 7. Just write that down right away. That's by the fundamental theorem of calculus. Okay, so I know that. Now I'll go back and read the problem again. F of x is given as this, and we want, whoops, you can't see the question here. Sorry about that. We want to find the equation of the tangent line to that function capital F of x at x equals 1. Well, again, I would have seen this function and immediately written down its derivative because I know that the fundamental theorem will apply here. Now, we always need, this comes back from pre-calculus, when you need to find the equation of any line, you need a point and you need the slope in order to find the equation of a line. Well, the function, we want the tangent line at x equals 1. So the point will be 1 comma capital F of 1. Well, capital F of 1 is the integral from 1 to 1. So that's 0. So the point handily is 1, 0. And the slope of the tangent line we know from Calc 1 is given by the derivative, capital F prime at 1. And, well, we knew we'd have to use this. It's the cube root of 8, or 2. So we have the slope, we have the point. We'll use the point-slope form of the line. y minus the y-coordinate of the point is the slope times x minus the x-coordinate of the known point. So our tangent line is y equals 2x minus 2. This is the answer to the question. The fundamental theorem has two parts to it. This is the second part. Let f be continuous on the closed interval ab, and let capital F be any antiderivative of f, not necessarily the area function, but any antiderivative. In that case, the integral from a to b can always be calculated by just plugging in the upper limit into the antiderivative and subtracting that function evaluated at a. This, by the way, is also written as capital F of x evaluated from a to b. It's another way of writing f of b minus f of a. The proof of this part of the theorem is very straightforward, so I think it would be good for you to see it. F is an antiderivative of little f, so we know that all antiderivatives just differ by a constant. So capital F of x is the area function plus some constant, where I'm choosing the area function to be the integral from a to x of f of t dt. So we know these just differ by a constant because by the fundamental theorem, a sub f is an antiderivative of little f. So we can just write f of b minus f of a and change f of b to a sub f of b plus that constant minus a sub f of a plus that constant. Well, you see that the constants cancel, these cancel, and a sub f of a is the integral from a to a, so that's equal to 0. And we have almost our result. We just have a sub f of b, but then again by our definition of a sub f, that is the integral from a to b of f of x dx. And that proves the theorem. This is the kind of problem that you will solve all through Calc 2 using antiderivatives. We could draw a little picture here. We're not going to need that really, but what does this represent geometrically? Well, it's the area under the curve y equals 1 over x from x equals 1 to x equals e. So we're looking at this signed area. We have no formula for that kind of region, but now we can use the fundamental theorem of calculus. All we need is an antiderivative of 1 over x. Well, we know from Calc 1 that the derivative with respect to x of the natural log of the absolute value of x is 1 over x. And therefore, natural log x, in this case we don't need absolute value because x is positive, we can say that this is simply the natural log of x evaluated between upper limit e, lower limit 1. Natural log e minus natural log 1. The natural log of e is 1 and the natural log of 1 is 0, so that shaded area equals 1. Another problem similar to the last one, it's number 33 in your text. Whoops, sorry about that. Part A asks us to differentiate the sine of x squared. Well, we know from Calc 2 that that will be the cosine of x squared using the chain rule times the derivative of x squared, 2x. So that's the derivative, and now it says to use that fact and the fundamental theorem to evaluate the integral from 0 to 1 of x cosine x squared dx. Well, what we want is an antiderivative, and we will just evaluate it between 1 and 0. What is an antiderivative of x cosine x squared? Well, if we just had a 2 there, it would be the sine of x squared. but that's fine because we know that we can pull constants in and out from the integral sign, constant factors, so I can multiply to the right of the integral sign by 2 and make up for it on the outside by multiplying by 1/2. Really, we've only multiplied by 1. Now I know an antiderivative for 2x cosine x squared. I have my 1/2, and the antiderivative is the sine of x squared. And we want to evaluate it between 1 and 0. That gives us 1/2 the sine of 1 minus the sine of 0, which is 0. So our answer is 1/2 sine 1. Just leave it in exact form. Every problem in 5.3 requires you to recall the relationship between a function and its derivative. So if you've forgotten this over the summer, look back to Calculus 1 material and make sure that you restudy the relationship between a function and its derivative. Review what you learned in Calc 1 and thoroughly understand and, yes, memorize the statement of the fundamental theorem. For the quiz, I would like you to practice problems 19 through 29 odds and definitely learn the statement of the fundamental theorem of calculus.